So welcome everyone to the Spectral Geometry and the Cloud seminar. It is the second installment for this season, and today we have the pleasure of having Gregory Berkolaiko from Texas A&M, and he will speak about towards Morse theory for dispersion relations, generic case, and the stage is yours.
Thank you very much. I have two little announcements. First, thank you to the organizers for keeping this wonderful event going through everything. And last week we were about to post a paper on arXiv, and one of the co-authors mentioned that we should really acknowledge the seminar because it's the seminar that brought us together and made our paper possible. So thank you guys. Second is my teacher. One of my teachers, Uzi Smilansky, today is his 81st birthday, so he's celebrating, he's not attending the seminar. If you're bored with my talk, take a minute, send him an email, pretend you remembered his birthday. All right, so this is joint work with I.Zelenko, who is also a professor at Texas A&M University. And it's a little bit different from the usual material that is presented at this seminar, but it has, I believe, very direct applications to the problems usually considered in this seminar. And it's kind of not spectral geometry, but it's geometry of the spectrum. It's the other way around. So let me first explain what the problem is very briefly, and then we will review the material that is needed to understand the results. So first of all, by sim n, I will denote the space of n by n symmetric matrices. Can be Hermitian or can be real symmetric. I will distinguish it by writing the field either R or Z or C, I'm sorry. And the eigenvalues are ordered. They're real, of course. And let M be a smooth compact manifold of dimension D. And we will be considering a family of matrices. So it's a map from the manifold to the symmetric matrices, which is smooth. So here I have, this is parametric family of matrices or operators. And M is my space of parameters. So what I would like to talk about is fixing K and looking at the kth eigenvalue of the matrix. This defines a function on M. The family is smooth, so the function will be nice, reasonably nice, continuous. And I would like to come up with Morse theory for this particular function, how it depends on K, so on and so on. So let me recall what is Morse theory very briefly, and then we'll go into it in a little bit more detail. So Morse theory connects the two things together. On one side, it takes the number and type of critical points of some function, of a nice function, smooth usually, or in the original theory at least, on the manifold to R. On the other side are topological invariants of. So any function, any nice function, the number and type of critical points have some information about the topology of the manifold on which the function is defined. So what are my motivation for studying this problem? The first motivation, very classical, is periodic operators. So if we have a periodic operator in RD, for example, or ZD, we do a FloquetBloch decomposition of it, and what we get is an operator that depends on quasi-momentum K, and quasi-momentum live in the so-called Brillouin zone, which topologically is a torus. So here M is D torus, D is the dimension of the space in which the operator was defined. Then we have this family of operators, and we can do lots of things with them. For example, we can study the bands of the continuous spectrum of the original operator by looking at the maxima and minima of the eigenvalue of this guy. So band edges correspond to global minima or maxima of an nth eigenvalue of f of k. Here, k is not the same k as before, sorry. Other critical points also play an important role. They're known as, they lead to so-called Van Hove singularities in the density of states. And actually Van Hove, in his original article, it was Physical Review Letters, or Physical Review at this point, he used Morse theory to prove the existence of Van Hove singularities. Very quick example, tight binding model for graphene. I'm not going to explain what it is, but I'm sure you have seen it. It leads to the following family of matrices, 2 by 2 matrices. It's not quite graphene because I'm putting different potentials on the A and B sides, and dependence on parameter quasi-momentum k is through these guys here, and here it's Hermitian. And if you, so this has 2 eigenvalues. If we plot these 2 eigenvalues for all possible values of k1, k2, we have this familiar picture. This is when A and B are equal. And when A and B are different, we have this picture. So the difference, the main difference is around here. So when A and B are equal, there is a conical point. The eigenvalues become non-differentiable around this point, at least as functions of 2 parameters. Here they are nice and smooth functions. So what I want to do is to, like, Morse theory would apply out of the box to a function that looks like this. But because of the non-differentiability, we have some work to do. And I would like to understand what is the Morse index of this point, basically, in this simple case. My second motivation is nodal statistics. You may have heard me talking about this quite a bit. So there is a link between the zeros of nth eigenfunction on a graph and the Morse index at 0 of the eigenvalue of a parametric family. So we start with Hamiltonian, we add parameters, and then at a special value of the parameters, there is a critical point whose Morse index gives information about zeros of the eigenfunction of the original Hamiltonian. Very cool. So this is proved in a couple of papers, in 3 papers actually, by myself, Yves Caland-Verdier, and Tracy Vayant. In this case, this thing is a magnetic Hamiltonian, but it's actually exactly the same thing as FloquetBloch Hamiltonian. But now the dimension of the torus on which the parameters live is not dimension of the physical space 1, 2, 3, but it is the Betti number of the graph, the number of cycles in the graph. So it can be large now. And here are some pictures for a graph like this. Basically, what I'm doing, I'm putting some magnetic flux through these holes. This gives me the 2 parameters alpha. And then I'm plotting eigenvalues, some eigenvalues like 6 and 7, something like this, of this graph. And this is the picture. It looks kind of complicated. It's touching things. The 2 things seem to be touching, but cannot be sure with numerical precision. What we're interested in actually is usually smooth critical points like here, or the one at 0 that is somewhere inside there that we cannot see. But there are lots of additional stuff like surfaces touching. This is zooming of one of these areas. So if we zoom in, there is actually a single point where they touch, the 2 surfaces touch. And these are not differentiable at this point anymore. So the hope is to understand if these guys are critical points in some sense. And if they're critical points, what do they contribute to this Morse theory connection between the topology and the number of critical points? And the hope is to prove some results that we conjectured with Lior Alon and Rami Bhatt. Another motivation is the theory of minimal spectral partitions that was brought to the forefront by Tiracini, Helfer, Hoffman-Ostenhoff, and since then there were a lot of work pushing this theory further. There, the manifold is the manifold of all possible partitions. That's a very complicated object, highly, it's infinite dimensional unless you're dealing with graphs. Even with graphs, it's a little bit complicated. But it seems like critical points are actually simpler than the underlying manifold, so that the information could flow a different way from the critical points to manifold. Quantum chemistry, another motivation. This is so-called Born-Oppenheimer approximation, where we say that a molecule has some molecular degrees of freedom where the atoms move around. But for each position of the atom, we can look and solve electronic Schrödinger equation. That gives us eigenvalue of the electronic Schrödinger equation, which we can treat as potential energy surface for the movement of the atoms. And surfaces like this arise, and then sometimes an electron can tunnel from the lowest point to a little bit higher level, and then it makes its way through the higher sheet, wants to go to the lower sheet, wants to go to the minimum. That induces rotation in space of the molecule, rotation in generalized way. It's oscillation of the molecule. There is a whole area out there with chemists doing these calculations. Very interesting, very complicated, because the number of degrees of freedom again depends on the number of atoms in your molecule. So it can the dimension of the underlying manifold can be very large. So M here is the molecular manifold of molecular configurations. All right, so these are my motivations. I'll not go in depth into them. Instead, I would like to give you a very short review of Morse theory, very informal review of Morse theory. So what is Morse theory? And if you have questions, please interrupt me better verbally. I can hear, but I cannot see the chat. So let's start with a function from the manifold to reals that is twice differentiable. What are critical points? The critical points are points where the second derivative of my function vanishes. If we have a critical point, we can further look at the Hessian, do the second derivative test to understand its type, minimum, maximum, something in between. The Hessian is the matrix of second derivatives with respect to all the variables. The Morse index is defined at a critical point as the number of eigenvalues of the Hessian which are less than 0. We assume the critical points are non-degenerate, so there are no 0 eigenvalues. And then this number is well defined. And we can form a Morse polynomial that's a formal polynomial in T. So T does not have any meaning here, just a marker variable. It's a generating function sort of thing. So we sum over all critical points and we take T to the power of the Morse polynomial. And Morse, one of the central results of the Morse theory is so-called Morse inequalities. So let me write them out for you. So we've defined this polynomial PF. To the manifold, you can also associate Poincaré polynomial of the manifold. If you don't know what it is, it's something you can look up for most manifolds. So something that encodes homology of the surface. Now, the difference of these guys, that's the theorem, is always divisible by 1 plus t, and the result of the division is some other polynomial with non-negative integer coefficients. So let me write it again. Pm of t is Poincaré polynomial of m. R of t is some polynomial that has non-negative integer coefficients. So basically, this guy provides the ground level for the number of critical points. You cannot the information in this polynomial is what's the minimal number of points by the type that you can possibly have. So let's do an example, very classical. I'm sure you've seen it before. So my M here is the torus, 2 torus. My function is just the height. So value of the function at this point is the height from the floor. Just imagine putting a donut on the floor. So this point is, of course, the minimum. This one is the maximum, but there are 2 other critical points, these guys. And at this point, you can go down this way, or you can go up around the circle. And this one, you can also go up or down around the donut. These are saddle points. So we have the following information. We have a max and Morse index at the maximum in 2 dimensions. It's equal to 2. There are 2 saddle points. Morse index in 2 dimension is equal to 1. And there is a minimum Morse index is equal to 0. So let's try to write what Morse theory is the Morse inequality. PF in this case is t squared plus t plus 1. So we just, for every point, we add a term t to power mu. Poincaré polynomial of the 2 torus is 1 plus t squared. We'll look it up somewhere. The difference is, of course, 0. So RT can be 0 in this case. By the way, I call it, or everybody calls it, inequalities, but this is an inequality. The inequalities are built into the coefficients of this polynomial R. Now you can say, well, we can deform the torus, or we can put a different function, which is the same thing actually. So we'll deform the torus, and the topology does not change, but the number of critical points changes. I will grow some horns for the torus, so I now have 2 maxima here. So how will the things change? There are 2 maximum. That gives me 2t squared. There is still 1 minimum, which gives me t to power 0. And there are alt saddle points, but now in here I have a new saddle point. So I have 3 saddle points. So saddle points give me 3t. So now PF is 2t squared plus 3t plus 1. So PF minus the Poincaré of the surface will give me t squared will remain, and t will remain, which is, of course, t plus 1 times t. So this is my R, and this is the thing we said it would always be divisible. The difference will always be divisible by. So what is it telling us basically is that, yes, you can create new critical points, but they must be created in pairs, because the result of creation must be divisible by this thing. So if you create a maximum, you must create another saddle point. If you create a saddle point, you must create another, either maximum or minimum, can go up or below, but it must be a critical point of neighboring index. Good. So, any questions? No questions. Let's go on. So what's the difficulty? What's the challenge in our work? The challenge, of course, I mentioned it already, is that the eigenvalues as functions of parameters in enough parameters, they're not smooth. So they're usually not smooth around points of multiplicity where two eigenvalue surfaces touch. And these points of multiplicity are often the most interesting points. For example, in graphene, this Dirac point explains some physical properties of graphene. So people want to understand those, count those as well. So we want to take care of them. And the question is how to define a critical point. It's not even the first derivative is not defined. So what's a critical point and what is its index? So before I give the definition, we can maybe look again at the pictures and talk informally what we want as a critical point and what we don't want as a critical point. So in here, like, look at the lower sheet. This one I want as a critical point. Why? Well, it's kind of a peak. It's not differentiable. Who cares? It's a maximum. I really want it. If we smoothen it, it becomes a bump, so it becomes a smooth maximum. It's stable situation under perturbation. I want this as my critical point. However, this case, two surfaces like this, they're a little bit sideways. They touch sideways. If you imagine smoothing them out, they'll separate like this, and this surface does not have any critical point, and this one does not have any critical point. They are both sort of increasing in some direction. So this guy, I really don't want as my critical point. Even though it's a singularity, I want to say it's not a critical point. So how do I define a critical point? Intuitively, the topological definition of the critical point is that the level curves undergo some topological change only around critical points. So that's the main idea. Let me draw some pictures. Well, imagine the level curves of a minimum. Below the minimum, they're empty. There are no level curves. Then at the minimum, we have a point, and then we have circles. So this transition from empty to circles is a change. At a saddle point, we have curves like this, and then they sharpen. And then after we pass through the critical point, they go the other way. That's also a topological change. At the maximum, we have circles, circles, circles until a certain point, and after that they disappear. That's a topological change. So that will be our working definition of a critical point. It's somewhere where things change topologically. It's better to deal not with level curves, but so-called sub-level sets. So let me define it. So x belongs to M. Point x belongs to M is regular for F if there is a neighborhood of x such that the following sub-level set. So it's set of all y's in U with values of our function that we want to study critical points of less than this value over here. So this is a critical point. This is all other points. So it's set of points where the function takes the value a little bit below the critical value phi of x. If this guy with minus is a strong deformation retract of this one with plus, then I call the point regular. If the sublevel sets can be deformed into one another. If they cannot be deformed, its point x is called critical. And this topological change basically is an obstruction to this deformation. Alexander, you have a question? No?
Yes, I have a question. If you take a smooth function that has a maximum, so it will not be a critical point with your definition, is that right? Because it will
no.
be
So maximum, this guy will look like this, and this guy will look like this without a hole, and the existence of the hole prevents this being deformation region.
Sure, thank you.
Thank you for the question. Right. So what's the meaning of the Morse indices? The Morse indices basically measure the topology of the thing we need to glue into here to make it deformation retractable. It measures the topology of the difference between these two sublevel sets. All right, let me state our main results. So some notation first. Sim nu is symmetric matrices of size nu by nu, with plus it's non-negative definite symmetric matrices, so 0 eigenvalues are allowed. With 2 pluses, it's positive definite, 0 eigenvalues are not allowed. The assumptions that x is some point on M. We're considering eigenvalue, the case eigenvalue surface defined on the manifold. And at point X, we assume it has multiplicity nu. So really, if multiplicity is 1, we can deal with it by normal differentiation. Generically, at least, the eigenvalue will be differentiable and everything will be fine. So really, we're interested in points of multiplicity here. But the theorem is still valid for all points. Now, at the point of multiplicity, I'll form a matrix U, which is basically a map into the eigenspace of lambda k. So I take all the eigenvectors, new eigenvectors, and I put them as columns into my matrix U. So it's n by nu. N is the dimension of the matrices. Nu is the multiplicity of that eigenvalue. I form this matrix. And then I form the following map. It's a linear map from the tangent space at M to symmetric matrices now nu by nu. So these guys, let me write it. They belong to sim n. So I basically reduce my matrix family to the eigenspace. So how is it formed? I take the derivative, I linearize my family, the derivative in direction v, so it's mapping from v to these guys. This is dependence on v, and I multiply from both sides by u. And now I have this guy is a nu by nu matrix. Okay. So the first theorem, it detects if a point is critical or not. So it's roughly analogous to the first derivative test. Let me write it out carefully. So I have this H, map H, and if range of H contains a positive definite matrix, or equivalently, the range of H orthogonal complement in the normal matrix scalar product, Frobenius scalar product, non-negative matrices, well, only 0. Then X is a regular point. These guys are equivalent. These conditions are equivalent. It's kind of intuitively clear, but it requires a bit of proof. This one may be easier to digest. This one is actually easier to apply because this guy is usually large, and this one is 1 or 0 dimensional. So you're just really looking at one matrix here. So it's usually easier to go compute the orthogonal complement and to deal with it. So that's for a regular point. For a critical point, we need to assume some transversality condition, some generic condition that I'll not go into at this point. And once this is assumed, the theorem is as follows. If range, it's kind of mirror image of the other one. If the orthogonal complement contains a positive definite matrix, or equivalently, range of H, X intersection with non-negative definite is just zero matrix, then X is a critical point. Let's do a couple of examples to understand this condition. It's actually quite intuitive, and to give you an idea, basically looking at the pictures, what is it looking for? It's looking for direction in which the eigenvalue kind of increases and still increases on both sides of the critical point. So on the maximum, it increases, decreases, but here it's increasing, and that's what we're looking for. That's what we're trying to detect. So basic example is not a degenerate eigenvalue. And let's, for simplicity only, take one-dimensional manifold. So it's a matrix of one parameter only. We can differentiate normally such things. So let U be the eigenfunction of the eigenvalue, and we want to form this guy, which is this thing. But if we work with it, so this U is just the one vector U. This is just the derivative of the matrix family. So we have our matrix family differentiated with respect to the parameter. It's just single parameter. On the right, it's multiplied by U. On the left, it's multiplied by U. And there is just one direction V, so it's just a constant multiplying V. So this map is multiplication by this scalar, and this scalar you will undoubtedly recognize as the derivative of the eigenvalue at this point. This is sometimes by physicists called Hellman-Feynman formula. So to go back to this thing, the range of this thing is either multiplication by this constant or multiplication by minus this constant. So if it contains a positive definite matrix, well, plus or minus of a number will contain positive definite number unless it's zero. Then it's a regular point. So basically, unless this is a zero, then it's a regular point. Otherwise, if it's zero, it's critical point. So it maps nicely to our usual definition of critical point. Slightly more advanced example, artificial but fun. So let's take the following family of 3 parameters, 2 by 2 matrices, 3 parameters X, Y, and Z. And I would like to look for doubly degenerate eigenvalues. Now, a 2 by 2 matrix is doubly degenerate only if it's proportional to the identity matrix. So basically, to find where these doubly degenerate eigenvalues live, I just need to equate it to identity matrix. So this guy is 0. And then because it must be diagonal with equal things on the diagonal, Z must be equal to 0. So we get these conditions. So in this 3 space, our M is 3 space here. The double eigenvalues lie on the curve. Curve has codimension 2. You probably expect that from Wigner-Neumann ideas. So let's try to apply the criterion. For that, we need to calculate the derivatives, the gradients, and then we do the directional thing. So these are derivatives of this guy with respect to X, with respect to Y, with respect to Z. Very simple. And then so we're combining these guys with coefficients and trying to understand the range of it. That's what the theorem demands. But let's not deal with the range, rather we'll deal with orthogonal complement of the range. So the dimension of the space of 2 by 2 matrices, real, everything is real here, is 3, right? Now this guy and this guy, they have a lot of constants, so they're linearly independent. df, dx, and df, dz are linearly independent. So the dimension of the complement of the range is at most 1. So we are looking at the range of these guys take up 2 dimensions already. So the complement will at most have 1. So the only way to have a critical point is that we need the orthogonal complement to contain some positive definite matrix. So we cannot have a dimension 0. So if this guy is linearly independent of those, that's it, we're done. It's not a critical point. So the only way for critical point to be is for this guy to be 0. That's condition for the critical point. Otherwise, dimension of the range orthogonal will be 0, and we're not getting critical. So this is 0 when y is equal to 0. We stick y equal to 0 here. Everywhere else it doesn't need. So then we compute the orthogonal complement of the range. A very easy computation. The matrix that is orthogonal to this one and to this one, basically. What form does it have? It is 2x over c minus 1 minus 1 2x over c. And now the theorem says we want to know if it contains a positive definite matrix. It's just one matrix. It's a span of one matrix. So we check if this one is sign definite or not, and calculate determinant, whatever x is. I skipped something. Y equal to 0. So sorry, I went too fast. Y equal to 0 means all our points of double degeneracy lived on this circle. But if y is equal to 0, they also must live here. So there are only 2 possible points, candidates for critical points. These guys. So x is equal to +1 or -1. We can substitute here, and we can find out when they are critical points and when they're not critical points. So critical points. So this belongs to positive definite matrices if C is smaller than 2. We can make some pictures of the eigenvalues of this. Well, it's 3 parameters, hard to make pictures. So I'm just cutting this space. I'm making the pictures in x and z variable, removing y. So if C is smaller than 0, these are the parametric eigenvalues, and intuitively it looks like critical points. If C is bigger than 2, these are the eigenvalues, and they look like they're not critical points. If you smoothen them up, it will be sort of increasing. If we look at the level curves, these are the level curves. They have some funny behavior. They're no longer smooth at this point, but topologically they don't change going through this value. Here, topologically, of course, we detect maxima, and there is also another saddle point, the smooth saddle point appearing here.
Gregory, does it hide somewhere Berry's face, your construction?
So very good question. So these are points, and we can look at the Berry phase around this intersection and this intersection. In both cases, the Berry phase will be non-trivial. So Berry phase does not tell us whether the point is critical or not. It just detects the singularity. So Berry phase will be the same.
Thanks.
Thank you.
Can I ask a question before I move on?
Sure.
So is lambda? Sorry, I missed the first 10 minutes of the talk. Is lambda k the first in the cluster? The index k, is it?
Any. For now, any. But I will. Good question. I'll get to the answer. The answer is 2 slides below.
Right. So I'm a bit confused by the.
Like in this example, you mean?
No, I mean in the theorem that you.
In the theorem, it can be any in the cluster.
And I'm a bit confused why only positive definiteness. For example, imagine that you are in the imagine that you are in the middle of the cluster.
Mm-hmm.
Then you have 2 situations, right? You can have the.
Let me carry on, because it will come up definitely, okay. And we can discuss it. But it's a good question.
Okay.
I'll just have more information.
Yeah. Okay. Intuitively, it doesn't seem obvious why only positive definiteness is the right thing to look at for middle ones.
Right. Yes.
But anyway, yeah.
Yeah, but I stand by my theorem. Maybe it will get more clear in the end. So let's come back to this question. This was the first derivative test. And now I would like to actually compute the Morse indices or whatever stuff can take its place at a critical point. So this is our second theorem, the more meaty one. But before we get to it, I'd like to talk a little bit about anatomy of the critical point, which we saw a little bit of. So if a point is critical, F is in general position, then there is a manifold, submanifold of M, along which the degeneracy will not separate. Roughly speaking, the picture is going to be like this, but that's a bad representation because I don't have enough dimension. So this green curve is the curve where the eigenvalues are double. This point is the real critical point that I'm interested in, because it looks like a critical point along the green curve. And there are also these directions in which the non-smoothness becomes obvious. So in general position, we know the codimension of S. Codimension of S is 2 if it's double degeneracy, 5 if it's triple degeneracy, and so on. This is Wigner von Neumann theorem, or Arnold also did, assuming real symmetric. In complex case, there is a formula as well. So the eigenvalue, when we restricted on this submanifold of constant multiplicity, it is smooth. When the eigenvalues don't separate, we can differentiate the whole eigenvalue group going together. It's smooth. And then along this submanifold, since it's smooth, we can compute the classical Morse index. We can compute the Hessian and everything like this. Everything is normal. So there are 2 directions. There is a direction along the manifold where eigenvalues don't separate, and there is transversal direction where non-smooth stuff happens. There is a whole theory by Gretzky and Macpherson, stratified Morse theory. And the main result of this theory is that Morse data at such critical point can be separated into a sum of the smooth Morse index and the transversal Morse index. I'm not defining this, it's a whole book that is devoted to the subject, but I'd like to give an informal sort of statement of our main theorem. Our main theorem is a little bit surprising, actually. It's that transversal Morse data is to a large extent universal. It does depend on things. It only depends on nu and on something that Misha brought up on the location of the eigenvalue that I'm considering in the group of the fellows that collide at this point, the lambda group. Not algebraic group, but the group of eigenvalues. That's the underlying message of our second main theorem, and it is not just universal. We can compute it exactly, but it is a little bit non-trivial. So I see I'm running out of time quickly, so let me switch to the other version of the slides that I should have posted actually. That has all the details filled in. I don't have time to write it in anymore. So for each critical point x, and k is fixed, the index, nu is, as before, denotes the multiplicity of this eigenvalue at the critical point, and I will denote this relative index that Misha alluded to. So if I'm looking at this eigenvalue lambda k, at different points, it may touch different surfaces. So here it touches things from above. So the multiplicity is 2, and the index, relative index from above of the black one is 1. Here it's in the middle of a group, so I is 2 out of 3. And here it's in the bottom of triple group, so I is 3 out of 3. This chi-I is the codimension formula that I mentioned already. Wigner von Neumann, maybe they didn't actually write the full formula, but it's the codimension of matrices with I-degenerate eigenvalue in the space of all matrices. So in particular, codimension of Sx in the general position is kappa nu. So there is some number. GR will denote the Grassmannian over field F. Field is either reals or complex numbers, depending on whether we're dealing with real symmetric matrices or complex remission. So Grassmannian is the space of all k-dimensional subspaces of F to power n, of the n-dimensional space. With tilde, this is the oriented Grassmannian. So here we just take the plane, doesn't matter the orientation. Here we distinguish the plane oriented this way from the other way. So it's a double, this one is a double cover. So here is our sort of second derivative test. It claims that the Morse inequalities remain valid with the correct contribution associated to the points that are not smooth. And the correct contribution has the following form. First, we take t to power mu. That's separating the smooth Morse index from the rest, and non-smooth is the universal. So this is not universal part. It can change depending on the family. The rest is universal. The rest of the contribution is this chi dimension, and then Poincaré polynomial of the correct Grassmannian, depending on I, real or complex Hermitian matrices. And here we have the oriented Grassmannian in minus the regular Grassmannian. So these guys, of course, you can guess they quite known, well studied, not very simple, well studied. So you can find literature, look up the formulas. So this gives the formulas that we need to stick in to make the whole theory work. I mentioned that Poincaré polynomials are known. Contribution of critical point of multiplicity is mostly universal, except for the classical smooth contribution. So non-smooth directions are universal. And this is how it looks. And indeed, for like middle eigenvalues, sometimes the contribution is a bit funny. So in a triple group, the middle eigenvalue the contribution of the Morse to the Morse count is 0, but I maintain that the point is still critical in the sense that there is some topological change going on. It's just not detected by this polynomial, which is a little bit crude. This is for a group. Again, in the middle, there is some stuff going on. Here is some zeros, but they're not fully zeros. So my claim is that the zeros are not completely zero. What does it mean? That means that, what do I mean? This is Poincare polynomial of something, right? Poincare polynomial does not detect the full topology. It only takes into account torsion-free groups in the homology. And if we include the information about torsion, sorry, out of time, but there is, you can add the generating function of the torsion. It doesn't really go into the Morse polynomial so well, but there is some stuff added to 0 that is non-trivial. And our idea is that why this stuff is there is that this torsion subgroups, torsion contribution, is the leftover of merged critical points. So if you merge the critical points, they can just disappear, or if the manifold was twisted sufficiently, they may leave a remnant which is not detected by Poincare polynomial, but instead comes up as this torsion, guys. And what you can think about is you can start perturbing your matrix and looking, so you unmerge the critical point. So here is a critical point of degree 3. If you perturb it, it falls apart into lots of different things. And the middle sheet now, over here, at least, and I think over there as well, over here it has a proper maximum. So there is a critical point. So here the point of the middle sheet is still critical in the topological sense, because it still remembers that it came from a couple of points that got merged together. This is not a theorem yet, if ever it will be. This is future work. So I think this is a good place to stop and to revisit maybe some Michael's question or other questions that you may have. Thank you.
Thanks a lot, Gregory, for this talk. We now have time for some questions. So as usual, if you have a question, either ask it in chat or unmute yourself to ask it.
Let me just quickly, thanks. I think it clarifies my question, but I'll have to think about it, and I need to teach now, so I might write you an email later. Okay.
I will send you a preprint when it's ready.
Okay, thank you.
Yeah, we did answer his question, indeed.
Thanks. Do we have any other questions?
Here's Alexandre. I'll try to ask a less stupid question than before. Do you know if this notion of critical point that you're studying is linked with other notion of critical point, like for maybe continuous functions or even for critical matrix?
Yes. So yeah, it is an excellent question. So there is a theory called Clark calculus or Clark differentials for continuous but not necessarily smooth functions, and that's what goes on under the hood. So we prove that the point is Clark critical, and there are some theorems linking Clark criticality to this more topological one that we need for the next theorem. So yes, it's linked together. Yeah.
Thanks.
Thanks, Alexandre, for the question. Do we have any other questions now for Gregory?
I just want to say that it's amazing work, amazingly presented.
Thanks. Thanks a lot, Peter. Yeah, I feel like this brings a lot of questions to me, but that are not fully formed yet. So I'll probably be sending emails in the next few days once they.
Thank you.
once they end up forming. So if we don't have any more questions right now, let's thank Gregory again.
And
Thanks a lot. We'll reconvene next week at the same time with a talk by Alessandro Savo. And yeah, thanks again, Gregory, for this talk.
thank you.